Alright, hello class. In this video, we're going to be kind of changing pace a little bit and talk about hyperbolic trig functions. I figured that after all of this series stuff we just slogged through, that something a little lighter would be nice to do as the very last lecture for the class. And that's part of why I chose this. It could have easily fit in an earlier section, but I find it a nice palate cleanser for everything we've been through so far. Okay, so what are the hyperbolic trig functions? Well, where the normal trig functions come from the unit circle. So the unit circle, radius 1, that's where our trig functions originate from. I think most people think of triangles when they think of trig functions, but actually they're truly defined in a more useful way using the unit circle and then expanding it to other circles. On the other hand, so we'll just say our normal trig functions come from here. Okay, from the unit circle. On the other hand, the hyperbolic trig functions come from the unit hyperbola. And I'm not going to go into huge detail here. It has to do with the area that's made by particular angles and how they intersect the unit hyperbola. But this is where the hyperbolic, and that's where that word comes from, because it's based off the unit hyperbola. That's where your hyperbolic trig functions come from. And the reason that they're called trig functions, well, one, we borrow a lot of the same names. We borrow sine and cosine and tangent and all of them. Of course, we call them like hyperbolic sine, hyperbolic cosine. But a big part of it is that they have a lot of the same properties. And we'll get into that in a little bit, but yeah, a lot of the same ideas, a lot of the same properties will hold between these two. Okay, so let's get into their definition and start sort of breaking these guys down. Alright, so the unit hyperbola is given by this formula here, that's x squared minus y squared is equal to 1. It's one of our conic sections. The unit circle, of course, is given by x squared plus y squared is equal to 1. Okay? And how it works, again, I'm not going to go into huge detail here, but just wanted to give a little bit of explanation here. Given, say, on the hyperbola, we do very much like we do with the unit circle. We create an angle, and that gives us a point x comma y, and we make the y coordinate our sine of theta, and the x coordinate is our cosine theta. Okay, we do something similar here. Whenever we cast an angle out, we're going to intersect this hyperbola at a point, right? And we let y be what we call hyperbolic cosine, or sorry, okay. Not sure what happened there, but our y value is hyperbolic sine, which we denote as sine h of a, and our x is hyperbolic cosine, which we denote as cosine h of a. Now, what is a? Well, a comes from the area of this region here, and that's actually a halves. Okay, so it's a little funkier. It's not as like 100% as straightforward as the normal trig functions, but it's still related, okay, to the unit hyperbola. All right, now thankfully we have a bit of an easier way to talk about these functions than trying to go to the area of the hyperbola and all that stuff. It turns out that hyperbolic sine h of x can actually be determined by this function here, e to the x minus e to the negative x all over 2. Or I like to sort of simplify this sometimes as 1/2 times e to the x minus e to the negative x. Okay? Then hyperbolic cosine, so these are often called, well, cosine h is often just called cosh, which kind of makes some sense. And then to kind of play off that, people often call sine h or hyperbolic sine sinh, so cosh and sinh. I'm not too sure about the sinh one. But anyway, the hyperbolic cosine is pretty much the same thing, but with a plus on the inside. So it's e to the x plus e to the negative x all over 2, also known as 1/2 times e to the x plus e to the negative x. All right, so there are our hyperbolic sine and cosine, and from here we develop the other ones just like we would in normal trig functions. So hyperbolic tangent, which is tan h, okay, is, well, our normal tangent is sine over cosine, and it turns out that a hyperbolic tangent is hyperbolic sine over hyperbolic cosine. Okay, which comes out to be, and this is why I like this more simplified form, 1/2 times e to the x minus e to the negative x all over 1/2 times e to the x plus e to the negative x. Okay, the 1/2s cancel, and we're left with just e to the x minus e to the negative x all over e to the x plus e to the negative x. Okay, so that's our hyperbolic tangent. Hyperbolic cotangent is just this flipped over, so it'd be cosh of x over sinh of x. Now we could go through this process again, but essentially it's just this fraction here flipped over, so it'd be e to the x plus e to the negative x all over e to the x minus e to the negative x. All right, then we have our hyperbolic secant and cosecant. So secant, well, remember, our normal secant is cosine flipped over. It's the same idea here. Secant h is going to be 1 over cosh. Okay, so that's 1 over, let me try that again. It's 1 over 1/2 times e to the x. For cosh, it's plus e to the negative x. Now, since we're dividing by the 1/2, we can flip that over to the top and get 2 over e to the x plus e to the negative x. Now, there are a lot of ways we could play with this and make it look a little different, but that's probably good enough. All right, then we have cosecant h of x. I wouldn't even know how you would start trying to give this one a nickname, but that's going to be 1 over sine h. Okay, and the same idea, same work, we'd get 2 over e to the x minus e to the negative x. All right, so here's all the definitions of our hyperbolic trig functions. And now I want to kind of show how they relate, or why we actually started calling them trig functions in the first place. And you'll start to see the similarities pop up almost immediately, and in basically every possible case. Okay, so for the sake of comparison, if we go back to our normal trig, and we look at the unit circle, which is given by the formula x squared plus y squared is equal to 1, what we end up with is, remember that x was our cosine theta, so here's our theta, and y was sine theta. So if we put this x and y back into this formula here, we'd end up with, well, the x squared would become cosine squared, and then the y squared would become sine squared. And this is where our Pythagorean identity comes from. It's the cosine squared plus sine squared theta equals 1. It comes from the fact that we're talking about the unit circle. And, you know, there are a lot of places where this comes from. With hyperbolic trig, on the other hand, we have sort of a similar idea happening. We still have the point xy, and here x is cosh of a, let's say, and y is sinh of a. Okay, and the formula for the unit hyperbolic is the x squared minus y squared equals 1. Okay, so if we do the same thing here, replacing the x squared with a cosh squared of a, and instead subtract the sinh squared of a, we should get 1. Now, you know, are we sure that this works? Well, let's see. Cosh squared of a would be the 1/2 times e to the x plus e to the negative x, and then we square the whole thing, right? So it would be 1/4 times e to the x plus e to the negative x, and this thing all squared. So if we were to FOIL this guy out, we'd get 1/4 times e to the 2x plus 2. Now e to the x times e to the negative x is just 1, so we'll literally just get plus 2, then plus e to the negative 2x. Okay, so there's our cosh squared. Our sinh squared gives us something very similar, since it's basically the same thing except with a minus sign on the inside. So when we square the whole thing, we'll basically get the same exact thing except with a minus on the inside. So we'll get 1/4 times be e to the 2x minus 2 plus e to the negative 2x. Okay, be good algebra practice to see if you could get these. You know, I'm trying it the long way, not just taking my word for it. Now, if I take cosh squared of a, and I just realized I put x's in here, so let me fix that. Let me just instead say that we're looking at x's as our variable here. That'd be easier to fix. Okay, so if I took cosh squared minus sinh squared, and put in what we have, so it'll be 1/4 times e to the 2x plus 2 plus e to the negative 2x, then minus 1/4 e to the 2x minus 2 plus e to the negative 2x. Okay, now we can take out the 1/4, and then we're left with, well, here, e to the 2x plus 2 plus e to the negative 2x. Okay, then here we have a minus affecting all of these. Okay, so we'll have a minus e to the 2x, a plus 2, and a minus e to the negative 2x. And all these e to the things cancel, and we're left with the two 2's. Okay, so what we end up with is a 1/4 times 4, which is 1, which is what we expected from the formula. The x squared minus y squared is equal to 1. Okay, so here it has a very similar identity. Okay, a very similar Pythagorean identity. Now, I don't think I would actually call this a Pythagorean identity. It's just something very similar. Okay, now, when we start taking derivatives, we're going to also see some more of the same properties show up, like we did here. All right, for example, if I take the derivative of sine h, well, that's the derivative of 1/2 times e to the x minus e to the negative x. Okay, well, the 1/2 just comes along for the ride. The derivative of e to the x is just itself. Derivative of negative e to the negative x, well, that's going to be negative and negative, so it will be plus e to the negative x, and we can't forget the 1/2 sitting out here. And look at that. That is hyperbolic cosine. Right? So the derivative of sinh is cosh. Well, that matches exactly because the derivative of sine is cosine. Right? Now here's where the difference starts to show up. It's still very similar, but when we take the derivative of cosh, right, we'll see it's the derivative of 1/2 times e to the x plus e to the negative x. In that derivative, well, the 1/2 comes along for the ride. Derivative of e to the x is itself. The derivative of e to the negative x is negative e to the negative x. And that is literally just sine h. Okay, so notice it's just like the normal trig, except a negative doesn't show up. Okay, that's interesting. Okay, I'll say same or almost same. So almost the same pattern. Right? In fact, it's almost a little easier because derivative of sine h is cosine h, the derivative of cosine h is sine h. Right? We don't have to deal with negatives. All right, let's start looking at some of the other ones. The derivative of hyperbolic tangent. Okay, well, we know that the derivative of normal tangent is secant squared, so let's see if we get that. Well, to start with, derivative of tangent h, well, that's the derivative of sine h over cosine h. Now, we could break this into the e to the stuff, but we already have the derivatives of cosine h and sine h, so I'm just going to go ahead and go straight to the quotient rule and say it'll be the derivative of the top, which is cosine h, times the bottom left alone, minus the top left alone, which will be sine h, times the derivative of the bottom. So the derivative of cosine h is sine h. All right, and all over the denominator squared. Okay, so this actually comes out to be cosine h squared x minus sine h squared x all over cosine h squared x. And this, as we saw before, that comes out to be 1. So we get 1 over cosine squared h, which is secant h squared, right? Secant h squared. So hyperbolic secant squared. All right, so that also matches. All right, let's do cotangent. So hyperbolic cotangent. There are a couple ways we could approach this one, honestly. I'm going to do it this way. Cotangent h of x, that's 1 over tangent h of x. Okay. And the reason I want to do it that way is because it will actually make it a little easier, because when you do the quotient rule, the derivative of the first guy of the top is 0. So really it's just going to be minus whatever we get here. So minus the top left alone times the derivative of the bottom. Well, the derivative of the bottom is secant squared x all over the denominator squared. Okay, and we could do it this way, like we did up here, but this works too. Just showing both approaches. So this is going to be negative secant h squared all over tangent h squared. Now, this might not this might not look the same just yet, but let's mess with this a little bit. Tangent h squared, so I have secant h, which is going to be 1 over cosine h squared. And then tangent h flipped over, that's of course cotangent h. So this will be cosine h squared x over sine h squared of x. So that's flipping this guy over, okay, and then rewriting this. So you see that the cosine h squareds cancel, and then we get negative 1 over sine h squared of x, which is actually cosecant h squared of x. Okay, so turns out we get the same exact pattern even with the minus. So what happens with tangent and cotangent, with the derivative of cotangent, the negative actually comes from the fact that we're using the quotient rule. Okay, in this particular case, not from introducing the derivative of sine, or sorry, cosine. Okay, next up, let's look at the derivative of secant. So again, secant h squared of x. Oh, no. So the derivative of secant h of x, well, that's the derivative with respect to x of 1 over cosh of x. Okay, so again, all of these reciprocal functions are going to use the quotient rule. Okay, so it'll be the 0 again minus 1 times the denominator. Whoops. Sorry. It's so derivative of the first, which is 0, so we don't have to worry about that. It's going to be the second piece is going to be the numerator left alone times the derivative of the denominator. So that's going to be sine h of x, and this will be all over the denominator squared. So it'll be cosh squared of x. Okay, and we split this one up so that it's negative sine h of x over cosh, okay, times 1 over cosh. I don't know why I keep adding squareds in there when I don't need to, but this will be negative tan h of x times 1 over cosh. That's going to be secant h of x. And check that out. It's a very, very similar rule, but a little bit different, because in the normal trig functions, we would have introduced a negative here and it would have made the whole thing positive. Here we don't have that, so because we're using the quotient rule, we end up introducing that negative and it doesn't get canceled away by introducing another one. Similarly, and I'll leave it to you to check that the derivative of cosecant h actually ends up being negative cotangent h of x times cosecant h of x. All right, so same process. Okay. All right, so here are all our derivative rules just hanging out all together. And from here, we can actually just reverse them to get integral rules. Okay, so, and I'm literally just going to reverse these. So the integral of cosh is going to be sinh, with a plus c. The integral of sine h is cosine h. Okay. The only thing we have to worry about is when do we introduce negatives and when do we not, and we have it's a different pattern. In the normal trig functions, it's just the co-functions that give us the negatives, while the non-co-functions don't. Here, I imagine it as a little triangle. We split it up, and these, like the top right-hand corner, doesn't introduce negatives, while the top left-hand corner doesn't introduce negatives, when the bottom right-hand does. So when we set up our integral rules, we'll just need to keep that in mind. So when I reverse this one, the secant h squared, that integral is just going to be tangent hx plus c. Okay. But here, if I start with a cosecant h of x, that's going to now, if I don't start with a negative, I need to introduce the negative with the cotangent h of x plus c. And that's how all three of these are going to work. Okay, so if I have the integral of just secant h tangent h dx, that's going to introduce a negative with negative secant h x plus c, and maybe I have the room to do the other one. The integral of cosecant h x times cotangent hx dx is equal to negative cosecant hx plus c. Okay, now from here, these guys pretty much satisfy all the rules you might expect. From here, the product rules hold, the quotient rules hold, the chain rules hold, use substitution holds, the whole 9 yards. Okay, as I said, I wanted to throw this one out at the end just to give you something like a little palate cleanser at the end of the semester, to something that kind of just harkens back to things that are a little simpler, from a little simpler time, right? We're not dealing with series or Taylor series or anything like that. Okay, so I'll do 2 examples here to just kind of refresh our memory on how some of these rules work, and then I'll show you what the graphs of these look like, just so you kind of get an idea of where these show up. Okay, so for this example, we want to take the derivative of x squared times cosh of the natural log of x. So this is a product rule within a chain rule. It's about as probably complex as I can make things. So derivative of the first is our 2x times the second left alone, then plus our first guy left alone. Now it's times the derivative of the second. So the derivative of cosh of stuff will be sinh of stuff. So remember, we don't have to introduce a negative here. So we'll leave the inside alone. Then we'll multiply by the derivative of the inside, which will be 1 over x. So it turns out we get 2x times cosh natural log of x plus x sinh ln of x. Right, I just simplified that. All right, so for this next example, we'll look at an integral. I have 1 over x squared times secant h squared of 1 over x. So this is actually a u substitution, and we can actually do a quick u substitution. By just taking, so I'm going to leave the 1 over x squared, right, the outside piece. I'm just going to integrate this, leaving the inside alone, and then divide by the derivative of the inside. So the derivative of secant h squared is the negative tangent h. I'll leave the inside alone, but then I'll divide by the derivative of the inside, and the derivative of 1 over x is negative 1 over x squared. And I'll have a plus c. And thankfully, these things cancel. My negatives cancel. So it comes out to just be a tan h of 1 over x plus c. All right, and here's what the two graphs look like. Here in the orange, that's cosh, right? And here in the blue, that is sine h. Okay, so what cosh models is actually, it will model how a wire will sit between two posts, right? So if I have a wire hanging from, say, two posts here, this gives an accurate representation of how that will sit. All right, and there are a lot of other applications that these functions lend themselves to. They pop up a lot in like fluid dynamics and other applications like that. So for this lecture, I think I'm just going to leave it there. There are a lot of things we could talk about regarding the hyperbolics, but as I said, I just wanted to let this be sort of a nice little way to send you off, whether that's off to differential equations or calculus 3, whichever class you're taking after this. So anyway, I will end it there, and I wish you luck in your future classes. So, cheers!